Hi, welcome back to Key Concepts in Technology. This is the introduction to week 7. This week we'll also have a video of a conversation with Evan Barba in the Communication, Culture, and Technology program. Evan has a great interdisciplinary background in computer science, HCI, robotics, and artificial intelligence. Evan and I will go over some essential concepts in computation and computational thinking. In this video lesson, I'd like to provide a framework for thinking about computation and software as artifacts of human cognition and intentional design, and help you think more about what software is and what makes it possible, and not simply how the specific products or apps that you may know work in single instances. Well, let's first do a little dive into the software all around us. How many kinds of software programs do you use in a day? At least the ones you know about. I say the ones you know about because we activate, engage, trigger, and get results from dozens of mini programs, computational processes running in the background, and built into things that don't look at all like a computer. Software built into microchips in our home appliances, entertainment equipment, smartphones, ATM machines, software always running in the background that keeps the internet running and continually updating itself. Software and chips connected to sensors that feed data to our cars, and software for interpreting ambient sensor data in the built environment of our cities and buildings. If you're not viewing this video outdoors, it's likely that the air you're breathing came from a software and microchip thermostat-controlled ventilation system. So instead of learning about computation and software by looking at machines, or computers as boxes of components for running software, we're starting with the mystery of the vanishing computer. That is, computers, computing, computation, software, all designed to disappear from view, instead of looking like industrial boxes in racks or on desktops, or like folding screens with keyboards. Computation is embedded in many other human-produced things. And where software isn't directly embedded in a chip in a device like in your media player, nearly all consumer and industrial products are designed, supply chain managed, manufactured, inventoried, and distributed with software. Everything from a Coke can to your Gap jeans are outputs of many stages of software-aided design and management. We're digital through and through. How is this possible? Well, here's where learning about computation and software as designs for automating symbol processes helps open up the black boxes. Having software and computation everywhere is based on key extensible design principles that begin with functions that aren't computational and give us outputs that go back into our human lived environment. Okay, let's consider the software we're more aware of and that has visible interfaces for mediating and implementing our everyday activities. You can see the software interfaces for writing text and documents and sending messages, for viewing and editing photos and videos and other kinds of images, for playing digital music through a mobile device or a computer. We use software all the time to do things, for enabling so many of our collective symbolic functions. Everyday communication, flirting, staying connected to friends and family, creating documents for work and school, reading, catching the news, enjoying entertainment media, shopping, and financial transactions. Note that all of these activities and social functions pre-existed computers. And have you ever noticed that all these software-mediated activities, in all of these cases, we never say we're operating a computer. Who wants to operate a computer? We want computers to get out of the way so that we can do real things. So in a very important sense, we're always controlling, triggering, and responding to software that's designed to stay invisible and black boxed. But to learn about software, we have to reverse engineer these black boxes and see how and why things work the way they do. Computation and software are the most transformative technologies we've yet invented, and they come from a centuries-long series of discoveries about how to use the symbolic abstraction features of numbers and words and represent them in electronic states that can be controlled and automated at incredibly high speeds. The amazing meta function in our symbolic capabilities has allowed the latest and greatest leap in human cognition and communication. Here's the trick. We can use symbols to not only represent communicable meanings, but to also represent other symbols. And even more, we can use one set of symbols to define actions to perform on other symbols. So, 3 steps. 1, we have symbols used as tokens for meaning, like everything we say, write, represent in math, or depict in images. 2, we have symbols that pop up to the next level to describe and interpret other symbols. For example, we use meta functions all the time in everyday talk about other people's talk, or we go up levels of abstract concepts in math represented in symbols. And when I say something like, my last sentence had 3 noun phrases and 2 clauses, I'm using the meta-language of linguistics, the language to describe language. And 3, symbols that don't represent any meaning, but define actions to take on other symbols. Now, this is the basis of most software. For this 3rd step, we've designed a logical bridge in electronics through binary base 2 math, 1 or 0, on or off, yes, no. So 1 and 0 in human symbols become coded as on or off, the presence or absence of a charge in electronics. And large arrays of these binary states can be designed to represent anything we want to represent. Now, take that principle of using symbols as operation definers with the instructions for encoding millions of transistors and digital microchips to register on and off states as directed. And we have almost speed of light electronic transitions that represent information being processed and keep other symbols in memory. And now everything convertible to digital information, from the sound waves in music to the physical conditions in our environment picked up by sensors, can be processed and transformed into symbolic representations that we can interpret and act on. Another great meta-symbolic trick at the core of computation is the principle of recursion, using a programming routine to call itself again to use the data that it just output as new input for further processing. All software outputs can go back into software for further interpretation. Now, every time we do a Google search, play a YouTube video on any device, or type text for a Twitter message, we're actually calling on hundreds of recursive software routines, the directives within a program, to process and reprocess complex symbolic actions that we activate and interact with. Now, in the software all around us, we've offloaded a lot of cognitive functions and agency to software agents. And software can also be designed to correct itself, to distribute information to other software on many other kinds of computing systems, and automate many kinds of processes without much human intervention, like all the software running behind the scenes that keeps the internet and all our telecom systems working. I framed our study of computation and computational thinking this way because I think you'll see why everyone should learn as much as they can about how software works and about computation, and the design principles that keep allowing us to extend what software can do. Even if you don't want to learn coding or be a programmer, you'll find many more things opening up when you learn what computation is and what's possible to do with it. This week, you'll have a chance to work through an online mini-course for an introduction to coding so that you can try out some fundamental computational concepts and see how they work in even really simple programs. Run with it as far as you can, and we'll talk about it in our online discussions.